All right, this is the first lesson for chi-squared, which is going to be our last unit of the year. So we're going to do a couple lessons on chi-squared and then a couple worksheets. And then on April 9th, Friday, the last day of the 6 weeks, we're going to do like a mini quiz situation for chi-squared. And then we're going to spend 5 weeks reviewing, doing mock AP tests, getting ready for the AP test May 17th. So, going to go over chi-squared today. So I got in Schoology, got a folder up and available there. Okay, so to start off, what is chi-squared? So we're going to do chi-squared test. So it's still a hypothesis test, except instead of testing for like a percentage matching what we think it should, we're going to test the ability to test like multiple percentages chance of happening. Like, is it too far gone with multiple things, not just like there's a 20% chance of this happening. It's like all these different percentages chances of happening. Okay, so I'm going to do a couple of examples. I'm going to go through the table we'll use and the formulas and we'll go from there. And then there is a worksheet on this. Okay, so let's use our example here. In 2014, Harvard was sued by Asian American applicants who were rejected. And so what we're going to do is we're going to test Harvard's claim here. So their claim is we only accept the top academic applicants and we treat those applicants equally. Our admitted class is as good as a random sample from the pool of top applicants. So we're going to see, does the people they accept actually represent a good random sample? All right, so here are the applicants from 2019. You had almost 58% Asian, 3% Hispanic, 0.8% African American, 38.7% white. So this is the applicants from 2019. So if it truly is a random sample of all of these, the people who were accepted, so does accepted match applied? So if it is a good sample, we shouldn't be too far off of these percentages. We shouldn't be too far off of this percent of people getting in. It truly does represent a good random sample. All right, so let's get into some numbers. All right, so that 2019 data had a total of 2,023 students admitted from those groups. So here is the observed. Here is like those 2,000 students. There were 432 Asian, 247 Hispanic, 226 African American, 1,118 were white. All right, so that's what we observed in 2019. What did we expect? All right, what did we expect? So your expected counts is the total amount that applied, or the total amount that were admitted, times the probability that they came up. So the total amount that were in our sample times the probability we expected, so the probability we expected of that group. So how many did we expect? Well, if it's a true random sample, 57.5% were Asian American. So what I would expect here is I would do 2,023 times like our total amount of students accepted times that 57.5% number. So if it truly were about the same, percent of people who applied and percent of people who got in, we would have expected 1,163. How about I just I'll go for the decimal. So 1,163.2. So I would have expected this many if it matched the true percentage. So if it truly matched 57% Asian American, then that would have been 1,000. And here's what we actually observed was 400 something. So something's not looking initially very good. All right, Hispanic was 3.1% Hispanic. So it's going to be, let me change here, 2,023 times 3%, so 0.031. So what's that number? That's going to be 62.7 students is what we would have expected, and here's what we observed. And what we expected. All right, African American was 0.8%. So 2,023 times 0.008. That's the 0.8% converted to a decimal. So we would have expected about 16.2 African Americans enrolled, and this is what we observed, 226. So both these numbers are looking higher. The Asian American number was lower than expected. And then the last one, white. So out of the 2,023 students admitted, there is a 38.7% white. So we would have expected 38.7 of those from our sample to be about 782.9. That's what we would have expected. Here's what we actually observed. So that number 2 is high. So all three of these numbers are higher than expected. And the Asian American number is lower. So it does seem kind of fishy from like Asian Americans thinking that they're like being discriminated against. The initial output of this is like, well, yeah, they are being discriminated. Like not a lot of them are being, as we would have, the percent applied compared to the percent actually got in is way lower. So we would have expected way different. Okay. So what we're going to do is we're actually going to test, just like what we did with hypothesis testing, like, well, how likely is it for these observed numbers to just happen by chance alone? Like, if these were truly the numbers, how far off are our observed values? Like, how crazy is that of happening? Like the question, is this dice unfair? So is the observed numbers, are these numbers super unfair? Do they prove anything? Okay. So what I'm going to do is, that's what we're going to do on the back side on number 3. It says write down a hypothesis. So the null, we're going to have a null and alternative still. So the null is that I'll say races are evenly admitted races are evenly admitted versus, like, what was it? The sample size? How did they put it in words? Versus the percent of races applied. So races are evenly admitted versus percent applied. So the key word is, the null is that they're evenly. Our alternative is that they're actually not evenly, because we think like the Asian Americans are being discriminated against. So the alternative is that races are not being, so not evenly admitted versus percent applied. So they don't match the percent applied. Like the people who are actually qualified and the percent of races applied, they should be evenly admitted. We're testing the claim that they're not evenly admitted. So that these observed values, we're testing the fact that this group of observed values is way different than what we would have expected them to be. Alright, so I'm going to test that. So what we're going to do is, let me just pull up the formula sheet so you can see what I'm doing. So formula, first page, at the bottom, we've got test statistic, confidence interval. Here is this thing. It looks like it's called chi-squared. It's actually chi. So chi is chi-squared. So chi-squared is right there. Let me zoom in. It's written with this like X-looking thing squared, and this is the formula for it. It's the sum of observed minus expected squared over expected. So we're going to go through this and how to use it. All right, so how far off are the expected versus the actual observed? Expected minus observed. All right, so this is what the formula sheet says is the chi-squared formula. Chi-squared, which is chi. Okay, so I'm actually going to plug this. So I'm actually going to use all of these. So let me go through maybe what this is first. So what we're going to do is we're doing how far off was the observed to the expected, and then we square it to make all of the numbers positive. And then you want to take it into how far off were we from expected. So that's why we divide by expected. So that's why we're squaring and dividing by expected. So I'm going to write this here and then give the number here. So I'm going to do observed minus expected squared over expected. So on the Asian American front, we observed 432 got in, minus we expected, we calculated that as 1,163.2. So I'm going to do observed minus expected squared divided by expected. So 432 minus 1,163.2 squared over 1,163.2. All right, when you do that, you get a pretty big number of 459.6. So we're going to go through what all these numbers mean. So we're just going to do it this way. So there's my Asian Americans. I'm going to do this for each one. So let me do it for Hispanics. I'll do the Hispanics in red. So here's the Hispanic. Maybe I'll do the Hispanics formula over here since I don't have enough room in my little table. So the observed Hispanics who got in, 247, minus, we calculated the expected frequency to be 62.7 squared divided by 62.7. So 247 actually got in compared to 62.7 expected to get in. So really big difference. What that comes out to is the number 541.7. So I'm going to kind of keep a tally over here. Okay, let me do, I'll do African American in green. Hey, I'm recording a lesson for when I'm gone. What do you need?
Keep going.
Okay. All right, so African American, we observed 226. African American, we expected 16.2 to get in, squared over expected 16.2. So when you actually do that, you get like this number over here. We're just going to pile them up. 2,717. And then the last one, I'll do the white column. So observed white that got in was 1,118 minus expected 782.9 squared over expected 782.9. And the calculator spits out 143.4. Alright, so you get those values. And then the formula, so the formula says it says this number or this symbol, which means to sum all of those things up. So then you add all of those things together, and that is going to be your chi-squared value. So when you add all those up together, you get chi-squared equals a massive number, 3,861.7. Really big number. Which you don't really want your like, if it's a huge number, it means that it was a really small chance of happening. We're going to look at the table. But that's my chi-squared value. It is a really big number. So the fact that I was this far off, like we saw, Hispanics, African Americans, white were way bigger than expected, and Asian American was way lower than expected. So this is my chi-squared value. This is my test statistic. I ran out of room on my board. Okay, so what we're going to do is we're going to use a new table, which is on the back side of the T table that we have been using. And I'm going to pull it up here real quick on the formula sheet. So what we're going to do is we're going to use this chi-squared value of 3,861.7, and I need to get a degrees of freedom as well. So degrees of freedom is going to be your number of categories, or like the people, in this case the races, minus 1. So we had 4 different races minus 1. So the degrees of freedom is 3. Okay, so if you still have your T table, on the back of it is this chi-squared number. So if you flip over, you keep going. So there's the Z table, Z, there's the T table. The very last thing on your formula sheet is this. You can see it has a x squared, which is chi-squared. So that's what we're going to do last here. Okay, so it kind of is going to work like the T table. Is I go to my degrees of freedom, and then I scroll over until I see my number. So we said we're doing a degrees of freedom of 3. And I'm looking for the chi-squared value of like 3,000 something, like a big number. So scroll over until you see 3,000. And our number is way less than this number. Way less than this number. So what we can say is our number is basically 0. Like, because it's less than 0.0005. So our chance of this happening, just by chance alone, is like 0% chance of happening. So what that means, if I kind of come back to this, the chance of me getting, if I truly expected this many Asian, Hispanic, African American, and white, the chance of me getting this different of numbers from it is basically 0% chance of happening, if it truly is a random sample. So there's basically a 0% chance of that happening. So then we actually kind of conclude like what we've done before. So like it's basically a 0% chance of happening, and 0 is less than 5%. So that means I do have evidence for the alternative. So lots of evidence. So evidence that percent admitted does not line up with percent applied. So like they are unproportionately giving it to white, Hispanic, and black, and not to Asians, compared to the percent of Asians who were like actually applied and they were worthy candidates. It's truly not a representative sample. It's not a very good sample. Okay, so what that means is I can statistically say that they're discriminating. Like they're not truly giving out their applicants a fair chance. They're giving it to too many white, Hispanic, and African Americans, but not enough Asian Americans. Okay, so that's kind of a big example with like these big numbers, because there's such a big difference between what we would have expected and what we actually found. So huge differences there. Okay, let me try something where we're not doing this chart. So taking that, re-look at the video. That's kind of your intro. Let's take this one as like, all right, let's get down to like, how would you actually do this? So if you didn't quite follow through that first one, rewind and watch it, but really follow through on this one, and you should be able to clearly see what's happening here with this table. So this is more like a typical problem here. So let's state our null and alternative. So the null and the alternative. So let's just look at what we're doing in the first place. So the question is, are births equally likely across the days of the week? So are births equally likely across the days of the week, or are births happening they're not equally likely? So that's going to be like our null, is this, that births are equally likely. So births are equally likely across days of the week. Okay, the alternative is that births are not. And so that means it could be Tuesdays are higher. I'm not saying a specific day, I'm just saying that they're not equally likely. Alright, so that's my null and alternative. Okay, so what we're going to do is these numbers right here are what we observed from our random sample of 150. Alright, so what we need is I need to say, what would I have expected on each of those days? I need to get my expected number. Okay, so how do I get my expected number if I think they should be equally likely among 1, 2, 3, 4, 5, 6, 7 days in a week? So if I think that there's a truly 1 in 7 chance of me having a Tuesday birthday, then I'm going to do 1 in 7, and that's what I should have gotten out of my random sample of 150. So each of those should have been a 150 over 7, which is, there should have been we would have expected 21.4 on Sunday, 21.4 bursts on Monday, 21.4 for each day. That's what I would have expected, is 21.4 bursts on each day. So that's what we expect to find. This is what we observed. So Sunday was really low, Monday was high, Wednesday is high, Friday is high, Saturday is low. So it looks like the weekend is really low. So is this enough to say that there's evidence people don't want to give birth on the weekend? It looks like, basically. People don't want to give birth on the weekend. Okay, so I'm going to compare all these different numbers at once to what I expected them to be. So I'm going to go to a new page here. So I'm going to calculate the chi-squared. I'm going to calculate the value of the chi-squared. So that's actually this one. So chi-squared, the formula is observed minus expected squared plus over expected, and sum them all up together. So I'm going to do it for each and every day. So if I kind of come back, okay, so I'm going to do it for Sunday. Let me do it for Sunday first. I'm going to do observed minus expected, so 11 minus 21.4 squared divided by expected. And then we're supposed to do the sum of all of these. So that's just what I'm going to do. I'm going to say plus, where's my next thing? 27 observed. So 27 minus 21.4 squared over 21.4. Yes, you put these in the calculator like this. Yes, it takes a little bit of time, but it's not that crazy. Yes, you need to write it all out. Okay, plus the next one. So I have to write 7 different equations. So plus 23 minus 21.4 squared divided by 21.4. Because I expected them to be equal, so all these expecteds are the same. Alright, plus the next one, 26. So Wednesday was 26 minus 21.4 squared over 21.4. Plus Thursday, 21 minus 21.4 squared over 21.4. Plus Friday had 29 minus 21.4 squared over 21.4. And then finally Saturday had 13 minus 21.4 squared over 21.4. Alright, so this is what we did in the chart on the Harvard example. I think it looks a little easier in this instance. So I just did observed minus expected, observed minus expected, observed. So all of these values are what I actually observed, and then the expecteds are all the same because we expected it to be the same. Okay, so I'll save you some time for the lesson here on plugging them in. But yes, you plug all of that into the calculator, and what you get on this instance is the number 13.6. Chi-squared equals 13.6. Alright, so what I'm going to do is then, just like the t-value, so I'm going to finish out my problem by using chi-squared 13.6. I need to know my degrees of freedom. The degrees of freedom is how many categories? 1, 2, 3, 4, 5, 6, 7, minus 1. So 7 minus 1, the degrees of freedom is 6. So I'm going to go to my table. I'm going to go to clear this. Degrees of freedom of 6. And now I'm going to scroll over until I get to 13, or I get in between. So here I am, 12 to 14. I'm somewhere in between these two is my 13.6 number. So what's my probability of happening? It's somewhere less than 5%, but greater than 0.025. So what I'm going to say is I'm going to say approximately 0.03. You could say 0.03, 0.04. How about we just say 0.035? As long as you say approximate, you show what you're doing, you'll be fine. So that's my p-value, 0.0, approximately 0.035. And then I'm going to compare it to my alpha of 0.05, so it's less than 0.05. So I have convincing evidence for the alternative. I have evidence that bursts are not equally likely. So I have evidence that bursts are not equally likely across days of the week. All right, so similar to hypothesis testing with means and alternatives and the nulls and all this good stuff, except what we're doing is we're actually testing like 20 different things at once. In this case, it was 7. I have a way of testing 7 different outcomes all at once in this thing called chi-squared, where I do observed minus expected squared, and it compares what I thought would happen to what actually happened. So there's also another thing you could do this with, like M&Ms say that there's 30% orange, 10% brown. Like you could say what we expected to get out of M&Ms compared to what we actually observed in how many colored M&Ms we got. So comparing multiple categories, multiple variables all in one test is what we're doing. So testing that out. This is a new topic, a little different. And so rewatch the video, rewatch this again, see it, and try it. And the more you look at it, the more you'll get it. There is a worksheet that I want you to do with this. There's some problems to test out, and yes, you need to write them fully out and try it. So for those of y'all that are in person, I have like a worksheet you can use, but there's a Schoology assignment.